Here is the integral derivation of the moment of inertia for a long, thin rod. If you rotate an object about a select axis, its moment of inertia will be the r squared weighted volume integral of its mass. Here is the setup for a long, thin rod rotating about its center. We set up a coordinate system around the rotational axis and break the object into differential masses along that length. We define the line density lambda as the differential mass over the length. If the object is uniform, then this density will be constant throughout. We are going to rearrange for differential mass and also substitute in for radial distance into our integral. The limits are taken from one end of the rod to the other end. Note that lambda, being constant, can be taken out of the integral. We solve the integral. Be careful with the negative signs and the exponents. And substitute back in for lambda. To calculate the moment of inertia for a long, thin rod rotating about its very end, the steps are very similar in breaking the object into its differential mass and setting up the integral. But now the limits of the integral have changed. Solve the integral with the new limits and again substitute in for lambda to get the new solution. Notice that despite this too being a uniform long thin rod, its moment of inertia is a lot greater because we have changed the rotational axis. As one final exercise, we will solve for the moment of inertia of a long thin rod with changing density along its length. The initial setup of the integral is the same as before, but now we substitute in for lambda before we take the integral. The solution now has two terms that depend on the constants of the density variation. To interpret the solution, you can check the extremes of those constants. In this example, if b is equal to 0, the second term disappears and we get back the uniform rod solution. If instead we make the first term disappear, we get a solution that is the equivalent of the moment of inertia of a thin wedge rotating about its pointy end.